But this is more for 128.
Hi, everyone. We have with us Ariel Gabizon, who is a chief scientist at Aztec Labs, and he's going to present this paper, visiting the IPA-sumcheck connection. So let's give it up for our speaker.
Okay, thanks a lot for coming. Oh, I think I'm echoing. No. Yeah. Yeah, this is a joint paper with Liam Egan, and I sort of browsed the seminar website, and I saw the topic of ranges is pretty broad, so I tried to make this presentation kind of pretty self-contained and basic. But I will start with a TLDR for people who are familiar. So basically the punchline of this paper is we reduce IPA verifier time from linear to polylogarithmic using the basefold multilinear polynomial commitment scheme, but on a polynomial with coefficients in a group rather than a field. So if that's totally clear, you're welcome to, if you have other stuff to do, you can spend your hours more productively. And I'll sort of spend the talk unpacking the words in TLDR. Beginning, with polynomials, so we're going to focus on multilinear polynomials, which are of great importance in ZK SNARKs. So by a multilinear, we'll always use this bold X for a tuple of k variables. And by k-variate multilinear polynomial, we simply mean polynomial of individual degree at most one. So for example, this polynomial. Only this, recently I started noticing that there's something confusing about this name, at least for me, because it is not a because of you allow a constant term, it's not actually a multilinear function, I think, at the, but this is what people call multilinear polynomial. So,
Yeah.
oh,
But like the presentation is from.
yeah, it's from here.
And this is just for getting the camera. You see, we've got like the camera.
Okay. All right. No, but it's not supposed to switch the slides.
No, it's not.
Oh, okay, okay. All right. So the most well-known useful multilinear polynomial that we will also use is the EQ polynomial, which probably a lot of you have seen. So this is a polynomial in 2 to the k variables, defined like this. So it's a product of these functions on the I coordinate of x and y, right? We think of our input as x and y. And the usefulness of this multilinear polynomial is that for any binary x and y, we'll have that EQ of x and y is 1 only if x is equal to y. And it will be 0 otherwise. And what we'll do a lot, which is a common thing, is we will look at an EQ polynomial when the first k variables are fixed to some Boolean z, right? So this LZ of x is the function that is sort of this indicator function that is going to be 1 on z and then 0 on everything else in the Boolean Q. So these functions EQ with the first input fixed, sort of a Lagrange basis for multilinear polynomials. So just to fix some notation, we'll always think of two parameters n and k. So n is like the sort of the size of the polynomial, and k is its log. It's the number of variables. And given a vector of size n, we're going to identify it with the multilinear that obtains the vector's values on the Boolean cube. And we'll use this notation f hat of z for the value of this multilinear at z. So f hat of z is just going to be the sum of EQI times fi. Where here, this first input should be a k tuple of values. So I'm just identifying an I smaller than n with like its binary representation. So that's what I mean by EQI. Okay, so basically we're always going to identify a vector of length n with the k variate log n variate multilinear that gets the vector's values on the plane. So a very important object in ZK snarks is what's called polynomial commitments. And roughly, a polynomial commitment scheme, the two most important components are, the first one is some commit procedure. So this will be some efficient procedure that, given a vector f, maps into some commitment f, and usually the commitment is much smaller than f. In our case, it will be like one group element. And the second, maybe more interesting part is some open protocol. So here, this is going to be some protocol between a prover and a verifier that both receive some input c to the polynomial, some output v, some commitment cm. So the prover and verifier both have this c, v, and cm. And the goal of the protocol is for P to convince V that Cm is really a commitment to a polynomial f such that f of z is equal to V. So, semi-formally, what are the requirements from BCS? The first one, like in any commitment scheme, you want binding. You want that, like an efficient adversary can't find two Fs mapping to the same commitment. And the second requirement is knowledge soundness, which means that if some efficient A can make V accept an open CMZV, with more than negligible probability, then in some sense we can formally define it knows, it knows an F such that the commitment of F is CM and F of C is V. Now, naturally, in practice, we don't run open as an interactive protocol. We use fiat shamir to just make it a non-interactive proof of F of C to B. And again, sort of what is desirable is that this, like the transcript of the protocol or the opening proof is much smaller than the size of the polynomial. Okay, so far, any questions?
Did you introduce the hat notation?
Yeah, so hat, I'm thinking of F as formally as a vector. And then F hat is like the multilinear that gets the vector's values on the Boolean cube. Or, more explicitly, for an input Z, F hat of Z will be defined like this. Okay. Any other questions so far? Okay. So, sorry, this is probably too basic, but important component for us will be discrete log hard groups. Specifically, what we're always going to have in mind is a group G written additively of the same size as our field, both having some prime size R. And right, what we mean by a hard discrete log group is that the way for us that's convenient to think about it is that if someone chooses uniform elements of the group, say n uniform elements of the group, and gives them to some efficient adversary, then the probability of A finding a non-zero F such that the corresponding combination of these group elements is zero is negligible. So it's a nice and easy exercise to see that this is equivalent to the more standard definition of discrete log hardness, where you just have like two group elements G and P, and you need to find the discrete log relation between them. Okay, so let's talk a little about yeah, by the way, just to get a feel, who here has before seen the notion of polynomial commitment scheme? Okay. So let's give a little tour of the landscape of polynomial commitment schemes, specifically for multilinears. For the history was that there was more focus on univariate polynomials, and it's shifted in the last 2-3 years more to multilinears. So roughly, almost all schemes fall into these 3 categories. Hash-based, which roughly means we're not using sort of any public crypto to construct the PCS. We're only using a hash function. And right, another setting is like we just talked, discrete. We assume we have a group with a hard discrete log, usually an elliptic curve group, but that's all we assume. And I don't know, for historical or social reasons, Polynomial commitment schemes based on discrete log hardness are called IPAs, which stands for inner product arguments. It's sort of a current convention. There's a lot of other inner product arguments, but only the ones based on discrete log hardness are usually referred to as IPAs. It's sort of a social convention, yes, right. And the third category is what we could call pairing based, where we assume we have a group, almost always an elliptic curve group with hard discrete log, but we assume in addition that this group is what's called pairing friendly, which we don't need to get into what that means if you're not familiar, but it gives you basically more power. And actually, you'll see a lot if you sort of follow Twitter, or you'll see that actually often people think of just two categories, like the hash-based and the elliptic curve-based, that includes both of these two. Yeah. So now let's look at like a few sort of parameters and how these three compare. So one important parameter is proof size, right? If you think of the open protocol as just one non-interactive message, what is it? What is proof size? And here the hash-based schemes are the worst. They're polylogarithmic, discrete logs, measuring, say, in field element proof size. Discrete logs are in the middle, and pairing based are the best. Another, maybe even most important parameter, some would say, is how much work does it take to commit to the polynomial? And the current, I don't know if this is 100% objectively true, but the current, at the very least, narrative, and seems to be empirical findings of most projects, is that the hash-based schemes are the best for fast commitments. So basically, in the hash-based schemes, the commitment consists of encoding your polynomial, thinking of your polynomial as a message, and encoding it in some efficient error-correcting code. And what people like about the hash-based schemes is you have a lot of freedom to choose the field you're working over and the code. So, for example, people have moved to work over fields that are like size 31, 32, like 2 to the 31, 2 to the 32, something of that order. So in the discrete log, the DL-based, the commitment consists usually of a multi-scalar multiplication over a discrete log hard group, an elliptic curve group. All right, so we'll see an example pretty soon. And in the pairing-based schemes, it's also the commitment is done via multi-scalar multiplication, but it has to be in a pairing-friendly elliptic curve group. And that requirement to be pairing-friendly and secure at the same time, it can sometimes slow down the efficiency of the group operations.
A multi-scalar multiplication is just multiplying many group elements with scalars.
Yeah, so I mean, we'll see. The commitment will simply be a Pedersen commitment. If your polynomial is f1 to f is f, and you have generators g to g n, and it's just some FIGI. Yeah, that's
it.
Yeah.
Of the three categories, is the hash-based post-quantum and the other two are not post-quantum secure?
Yes.
Okay.
Why is computing some FIGI slower than running some, is that an error correcting code?
Yeah, error correcting.
Yeah, it feels like the error correcting code would be more complex. Or is it?
Yeah, that's a great question. That's why I said at the very least the narrative right now is that the hash base are the fastest. It's not, so one reason I think why people are getting good empirical results over, over here is that, right, to get a hard discrete log, you need to work with a group of size like 2 to the 256 to get it, right? Because of Pollard-Drove attack, you need a, so you're doing, so that's the scalar, that's the size of the scalar field of the group, and you're working over that field. So even if you're input polynomial, in many cases, it's like, it's all zeros and ones, you're forced to work with a field to do operations in the scalar, like, well, certainly, like, well, your operation will be over the base field, it'll look the curve, and it will be of, yeah, also size, like 256 bits. Whereas here, people are lately seeing, oh, we can work with a field of like 32 bits. I think that is the one big reason why. Asymptotically, right, if you, right, you do have linear, I mean, people are using Reed-Solomon in practice, but you do have, which is n log n time, you do have, at least in theory, you have codes with O of n encoding time. And in DL, right, the MSM, you need to use this thing called Pippinger, which gives you something like lambda n over log n. And in lambda over log n, you have to take it to be like super constant. I mean, in practice, everything is constant, but lambda, theoretically, lambda over log n for security needs to be super constant. So it is true, theoretically, this is the only place we know to get like linear time. Although in practice, people are using Solomon, which is not log n. But still in practice, they're getting very good results here because of the ability to work with small fields. So another important parameter is, of course, verification cost. And here there is a big sort of caveat or barrier to using the discrete log-based schemes. Their verification requires an O size, not only the prover, but also the verifier needs an O size MSM. So, right, this is a big barrier to using discrete log-based schemes. But there's been a few years ago, there was a very, I should have credited the sort of the Halo paper here. So a big mitigation to this is the sort of the noticing that in many use cases, where we're not verifying one proof, we're maybe verifying, like we have a ton of sort of client snark proofs being propagated in a network that need to be verified on some chain. And verifying these proofs, it reduces eventually to verifying some polynomial commitment opening. So we're not really interested in the cost of verifying one proof, we're interested in the cost of verifying 1 million proofs. So then the question is like, well, is there some way to reduce checking several evaluation claims without actually having to do the verification? And here there was this very nice observation, first in the Halo paper and subsequent papers, that if you just need to accumulate evaluation claims and defer the verification for later, you can do this in O log and verify. So, basically the DL schemes in many parameters, they sort of occupy a useful middle ground between the hash-based and the pairing-based. And this accumulation thing is, it mitigates their drawback pretty nicely, but still it would be nice to improve that, get rid of that drawback, and sort of that's the point of this work. Basically, that we reduce the discrete log, also the final verification time to a polylog.
question.
Yeah,
Maybe this was already covered, but so it looks like the hash-based ones are. What was I gonna say? Like less good than the other two, just based on these tables. But is there any is there any dimension where the DL-based ones beat the pairing-based schemes?
the DL based beat the pairing based in faster commitment. Because you don't need a pairing friendly group, which can be slower. They also have the advantage of not requiring a trusted setup. Yeah. We have like, the reason we use, there's also this other aspect that to efficiently use, at least like what we're doing right now in Aztec, to efficiently use a pairing-based scheme, you need to work also with the discrete log-based scheme. This has to do with how recursion works in elliptic curve-based schemes. There's this need to use need is a strong word. But there's this desire to use what's called a cycle of curves. And then in this cycle, you'll have your main curve is pairing friendly, but your second curve is not. And then just to recurse sort of on the pairing friendly curve, you do need to operate on this curve that on the system that is DL based. That was a lot of details in a little messy way. I don't know how to figure it out. But yeah, just try to say it like in terms of our main reason for working with the DL based scheme is that it helps us get fast recursion for the pairing based scheme. All right, so now to present, like, explain a little of our, of our construction. So the important component is going to be the SumCheck protocol, which I won't. So I don't want to, go through what it does. I just want to sort of go over what it gives you. So suppose you have some k-variate, not necessarily multilinear polynomial A with individual degree D, and you have some target value C. And P wants to prove to a verifier that the sum of A's values over the Boolean Q is C. So what usually it's useful to think of the SumCheck rather than a full protocol as a reduction. And the protocol, the SumCheck protocol reduces checking this to reduces a sum to a single point. So reduces checking the sum to checking just that A of R is equal to V for a uniformly chosen R. Has anybody here never seen the SumCheck protocol?
You can ignore me for
So, yeah, in any case, we can all think of this just as a black box that reduces verifying a sum to verifying a single evaluation. And the point is, right, the communication of that in the protocol will be basically logarithm. Now, usually, we think of the SumCheck protocol as working over the field. But what was noticed in this paper of Bootle, Chiesa and Sotiraki, if I'm saying that right, that you can think of the SumCheck as operating over polynomials, over groups and rings and modules. And specifically, we're going to look at polynomials over our prime group. So, right, what does it mean to look at polynomials over a group? So we just mean, like by polynomial, we just mean a formal expression, some AI x to the I, but now our AI is the group element. And such a polynomial, it can be evaluated over x in the field. So the input of the polynomial, we're still thinking of it as over the field. Because, right, if we substitute the variable x by x in the field, this AI x to the I is well defined because it's scalar multiplication between the scalar x to the I and the group element AI. And therefore, this sum is defined. So we can evaluate a polynomial over a group at an x in the field. Right, remember that our field and group, they're of the same size, so that x in the field exactly fits as a scalar. So it's easy to check that the regular Schwarz symbol holds, right? Remember here, everything is prime. The group is of prime order. Field is of prime order. That is, a non-zero polynomial will be zero at most dx's in the field. We can add polynomials as usual. We just add, right? We'll add the coefficient of x to the I. Right, so this would be addition to the group. And the more interesting part is we can multiply. This is where we can multiply a polynomial over the field with a polynomial over the group. Because, so say that these AIs are in the field, these BIs are in the group, and now we multiply and we batch the terms as we usually do. So this will be the coefficient of x to the L. And this coefficient, some AI Bj, is well defined because we're always just multiplying an AI in the field with a B in the group.
This is from BCS21.
Yeah. So now basically we're going to go over the inner product argument from the bulletproof paper, but we're going to as done in BCS21, we're going to view it as a sum check over a polynomial with coefficients in the group. So specifically, we're going to look at a multilinear polynomial commitment scheme based on Bootle proofs. So first, we're going to have a setup stage where we're just going to choose a bunch of random generators. And now what's the commitment going to be to a vector f? It's just going to be the Pedersen commitment with the generators gi, just sum fi gi. And now the more interesting part is how we do an evaluation. So again, what do we want? We have some commitment Cm, some input Z, some value V. And we want to prove that Cm is a commitment to a polynomial f with f of Z equals V. So this is where you need to do some sort of typecasting in your head. We're going to look at the following polynomial over the group. So the main thing to sort of typecast is, right, we chose these n generators for our Pedersen commitment. And now we're thinking of G hat, the multilinear with coefficients in the group whose values on the Boolean cube are these n generators, right? So this is G hat. So we're looking at the polynomial f hat times G hat plus EQ xz, so we're fixing the second argument of EQ to Z, times f hat x times P. And we need to sanity check that we're not multiplying two group polynomials, right? And we're not, right? This f is in the field, G is not. EQ and f hat, they're both over the field. So we're allowed to multiply them by sort of the constant polynomial, which is the generator P.
Why is it disallowed to multiply two group polynomials?
Because it's not defined, right? So if we go back here, right, when you try to define the product, so the coefficient of x to the L will be like, right, this sum. And if you had an AI and BJ both in the group, you wouldn't, right, that wouldn't be defined. But if you had AI and BJ both in the group,
Oh, I see. It's an additive.
It's an additive group, yeah. So let's see what the sum of, say, when the claim is true, the commitment of f is Cm and f hat Z is V. What does the sum of this polynomial over the Boolean cube look like? So it's sum f hat of B, G hat of B plus EQ BZ f hat of B P. Now these values f hat B, G hat B, right? They're just the fi, the values fi gi. So the sum over fi gi is just going to give us Cm. And the sum, right? What is the sum of EQIZ fi? Forget the P for a second.
FC.
Right, exactly. It's just by definition FC. So we're just going to get Cm plus f hat of C. Now, the interesting exercise we can do for a second is the sort of the other direction. Let's think about it for a minute. So suppose we know that the sum of A is CM plus FZP. Does that imply this claim? Like, does that imply that COM F is CM and FZ is V? Oh, sorry, say, say the sum was CM plus VP. Does that imply that COM F is CM and FZ is V?
Can I repeat what is P again?
P is simply a random group element
Oh,
we chose in the setup.
Otherwise it breaks the log assumption.
Exactly, yeah. So, right, so what, break it down a bit, right, it's clear, like, say we had, instead of this one sum, we had two separate sums. We had this sum, FBGB, and we knew it was equal to CM. And we knew separately that some, this part is equal to F2V times T. Right, then just by definition, it would mean that COM F is CM and FZ is V, just by definition. But we don't have these, we don't know that these separate sums hold, we just know that the combined sum holds. But if you can sort of, what you can see is, if at least if an efficient adversary would find F such that the combined sum is equal to CM plus VP, but the separate, like the first part isn't equal to CM and the second part isn't equal to the VP, then you would find a counter example. Discrete log. So I guess it's a lot of details, but the point is, it's enough to prove this evaluation claim. It's enough to prove that the sum of A is equal to CM plus B. So we can run a SumCheck protocol, right? But the SumCheck protocol, like we said, we're just thinking of it as a reduction. So the verifier still needs the end of the SumCheck protocol to evaluate A of R. And the question is how it does that and if it can. So let's go over the components of this A of R. Well, EQRZ is, so basically in the regular sort of bulletproof protocol, V will compute EQRZ and G hat of R. I mean, okay, so putting efficiency aside, right? It knows the generator, so it can compute G hat of R. But then the question is, like, okay, how, it also needs to compute as part of A of R, this F of R. And how can it compute it? It doesn't, I mean, that's the whole point. We want a scheme to evaluate F, and verifier doesn't have F. And the strange thing is that P can simply send F of R. And the sort of the strange and useful thing is that when G has hard discrete log, you can prove that that this is sound. And that even though the prover is just choosing a value that is supposedly F of R at the end of the protocol, right? So it can be very adaptive, seemingly. This is still sound. It doesn't break.
How can the verifier compute G of R efficiently?
Exactly. Great question. So here you exactly point out the drawback of the classical sort of IPA that computing G of R is a size n MSM for the verifier. Specifically, this is what G of R looks like. So so the first thing, as like I sort of said before, you can use the fact that the G hat of R is of this form to efficiently combine, like if you have many evaluation claims, G of Rj equals Bj, you can efficiently, since time is short, I don't want to talk too much about the accumulation part. So put that aside. So yeah, say for final verification, what's left is really to compute this value, G hat of R. And again, in the classical sort of bulletproofs IPA, this is just a linear time verifier. And what sort of we observed in this paper is that if we have some, say, multilinear polynomial commitment scheme for field values, multilinear polynomials, but where all operations are linear, both the prover and verifier are linear, then we can simply run the same PCS on a group value polynomial. And specifically, we use a sort of a group variant, the basefold multilinear PCS. Basically, in our scheme, the prover will send a basefold, or the prover and verifier will use basefold or a group version of basefold to prove that the value of G of R is correct. Now, I thought to say a few words about how basefold works, but I don't know what the time. Oh, 10, that's a lot of time. Okay. Before I do that, any questions before I do that? All right, so yeah.
Maybe just clarify, so you're suggesting that you can run basefold here on group value multilinears?
Yes. Yes. That is the main point of the paper. Yeah. Okay, so I'm gonna give you, yeah, little of a feel of how, well, some combination of Fry and basefold works, because basefold is very much based on something called the Fry protocol. So now let's think of our vector of generators as we thought of it as a multilinear. Let's think of it for a second as a univariate. And now let's send, the first thing we're gonna do is we're gonna send a Merkle tree commitment to
Sorry,
the,
so just to be clear on the definition of this polynomial, so you've got coefficients that are group, just using additive group notation so.
additive.
Okay, and the variables, are these they're scalars, the variables are field elements or?
They're evaluated, yeah, the variables are scalars, like you evaluate the polynomial at field.
Got it, yeah. Okay. So like when we say x to the I, x is out of the group, x is scalar field.
Well, X is a variable, but you're gonna evaluate it, yeah, you're gonna instantiate it as a field element.
Got it.
So we're gonna send a Merkle commitment to the values of G on a 2n order subgroup in the field. Yes. And now let's recall we have, as usual in FFTs, we
So like technically, we're looking at a vector space, right? Because
right.
so like the
Yeah. So, right, and as you've probably seen many times in FFT, right, we can decompose our univariate little g as g even of x squared plus x times g odd of x squared, where g even and g odd have half the degree. And now let's look at the following. This is a kind of the key component of the Fry protocol, and I guess part of the basefold protocol. Right, we had our evaluation point that we wanted to evaluate the multilinear at R. Let's call it R1 to RK. And let's look at the following fold operation. So to fold, we want to fold G and get a univariate of half the degree. So to fold G by R1, we're going to look at the polynomial at this polynomial, 1 minus R1 G even plus R1 G odd. Okay, and now, so this is a polynomial of degree n over 2. Now we're going to have P send a Merkle commitment to the values of G1 over an order n subgroup. And we're going to have the verifier. So right, so we've sent these two Merkle commitments, where the second is supposedly this folding of the first, but we don't know that for sure. So the verifier is going to check at random spots that really G1 is the folding of G by R1. Right. So an important point here is that one value of the fold is really is a sort of a local thing. It's a combination of two values of the original. And now there's this nice thing in the correspondence between the multilinear and the univariate. If we look now at the right, so we look at the vector of n over 2 values of G1, and we look at the coefficients of G1, just the coefficients in monomial base. There's a lot of type conversions here. And now we think of it as k minus 1 variate multilinear, right, by the corresponding k var. Then G hat of R, what we're interested in, is gonna equal G hat 1 at just R2 to RK. So if G hat 1 is the correct fold, we've reduced the evaluation problem by half, sort of. And of course, what you do naturally in Fry is you just sort of k rounds of this until like you don't need to send Merkle commitments. You can send the whole GK and in the plane sort of. Remove this a bit. But okay, and now it's sort of the question that a lot of research has been around the last few years is like, how much do these random consistency checks between G and G1 really ensure the soundness of this whole thing? And this very interesting thing called the correlated agreement theorem of Ben-Sasson et al. It shows that with very good sort of parameters, this scheme is sound for random R. For random R, most R's, there'll be some bad R's, but for most R's, this will work. This will work well. Okay, but right in the definition of a multilinear polynomial commitment scheme, we wanted something that is sound, right? That works for all evaluation schemes. So we need something that sort of reduces all evaluation points to random evaluation points. Right? And sort of like we said, right, this is the sort of thing that SumCheck does. So this is right, a central idea. There's other various ideas. This is a central idea in the basefold paper that by interleaving the well-known Fry protocol and the SumCheck protocol, doing the first round of each, the second round of each, we can get a multilinear PCS. Okay, so I think I'm probably pretty close to time, and yeah, I think I'm. So yeah, I'm again a little outside. So see the paper on Uprint for fuller details. Yeah, thanks. Any questions?
So, these polymorphisms usually hide some one of the factors. I was wondering, to run these in practice and actually solve some benefits, or
I haven't run this. I haven't run this in practice yet. Yeah. I expect around, so right now, like in our system, we're doing this very big multi-scale multiplication. We're doing what's called in circuit. And for our sort of sizes, I expect like a 4x improvement to totally improving kind of the whole system. But, we haven't done any this.
or you plan on using it for what?
We're not sure yet. Like, we're sort of we're not sure yet. We're sort of in a phase where we're trying like not to change things till the maintenance through. So yeah, I don't know. Use it.
So it's a 4x improvement over what? What is the current? Is it bulletproof?
So, sorry?
Is it bulletproof? Is it fast-paced? What is
Yeah, so right now, I mean, this is part of a lot of recursive proofs, but basically we have at the end of our what's called roll-up, we have inside a circuit, we're doing this multi-scalar multiplication of size 2 to the 16, which corresponds to the final verification of bulletproofs. So the 4x is my estimation of if we instead in that circuit, we would do a verification of basefold, right? Which mainly most of the work there are these Merkle paths. That would be the reduction in the circuit size.
So it's over bulletproofs. So right now you're running bulletproofs, right?
Right now, we're running like bulletproofs with Halo, so sort of, so we're doing aggregating and yeah.
Let's thank the speaker again.